Hello everybody, my name is Thomas Maris. I am an associate professor of medical physics here at the University of Crete. We're about to show you the basic quality control tests for an MRI system, a clinical MRI system, the system you hear. This will take approximately 3 hours. It's going to be a real presentation of the quality control test. We're going to do it actually in a way that we think we're going to do it in the easiest way possible in order to see and understand the whole procedures. Okay, let's start by introducing the MRI system to you. Actually, this system is an old system. It's a 1.5 Tesla magnetron vision sonata hybrid system. In fact, it is a 1.5 Tesla with enforced with powerful gradients. We're talking, our gradients is 45 millitesla per meter, the strength, and 200 millitesla per meter per millisecond, the slew rate. We're going to check and make the basic control test, the basic quality control tests. But first of all, I would like to introduce my colleague to you, Ms. Katerina Nikiforaki is my PhD student, and together we're going to share this whole issue.
Hello everybody, thank you Dr. Maris. Let's start the quality control by showing the phantom. This is the phantom that we will use. It consists of multiple compartments. Each compartment is designed to perform a specific test and will permit us to complete the whole QA test.
This phantom is known as the American College of Radiology phantom, and actually it's been designed for doing multiple tests using one tool. Under this assumption, the first thing we have to know is how to correctly position this specific phantom inside the machine. So the first we have to know is the center of the object. The general philosophy is to actually try to have 4 points in space, to have 4 points in 1 point in space.
Aligned. To coincide. No.
So we have to have that. Okay, we have to have 4 points which have to coincide in 1 point in space. These 4 points are actually what? The center of the object. In this case, the center of the phantom. The second point is the center of the magnet, which is called isocenter. The third point is the point of the coil we're about to use, we're going to show. And the fourth point is the center of the scan, which we're going to do afterwards. Starting by this. The center of the phantom, for this specific phantom, you can put it in this way. You have a mark there, which is called the notice line, and you can also have a mark in the front side. So this is assumed to be the center of the phantom. As I told you, we have to have the center of the phantom to the center of the coil. In order to do this, we have to use specific tools, these sheets of paper, simple sheets of paper, which are made by wood, we all know that. So we have to put these sheets of paper in this point, in this size. We check the size actually in order to be at the appropriate position. And then we have to shift and put the phantom on the base of the head coil. Actually we're going to check, we're going to do the test using only one coil, the head coil. We're going to talk about this later. Another important issue is the level. We have to use the level in order to be able to align with the axis of the magnet. Having said that, first of all, I have to actually define the axis. You can imagine that the magnet is a barrel, that's the point. So we assign and we define this axis, which is the left-right axis, as the y-axis, as the x-axis. The anterior-posterior axis is the x-axis, and this axis is the z-axis of the magnet. So practically what we have to do is that we have to coincide 4 different points in space in 1 point in space. Point is like this. These 4 points are, again, the center of the anatomy, the center of the phantom, actually, the center of the coil, the isocenter of the magnet, and the center of the scan. Under this rationale, actually, the first thing we have to do is to position and find the center of the scan. Okay.
It is difficult to underestimate the importance of correct positioning, as it can improve SNR by a factor of 2. Correct positioning is really important.
totally agree with that. So in order to be able to perform this thing, we have to put all the objects at the center of the field. So
in this particular phantom, we can see that correct positioning means seeing the laser point in the edge of the plastic test object inside the phantom.
We know that this thing, and this is exactly the marker. We have to have the line at the edge of this object inside the phantom. So under this, we have to use the lasers. We assume that the lasers are calibrated. That's very important. It's another check for that. But anyway, for the time being, we think that the lasers are calibrated. So the lasers tell the truth about position. We use the lasers. We put the lasers at the specific position here, and then we're ready to cover the phantom with the coil, with the rest of the coil. We already have the markers in the coil, so we know that this specific position is at the center of the half edge of the coil.
Let's check the alignment now.
Seems to be okay.
It seems to be okay, yes.
That's all right. And if everything is okay now, it's the time to actually cover the rest of the coil with the extra part of it and close the head coil. A good view now, prior to start, is that all this cylinder is at the center of the extra cylinder of the phantom. So if you actually check with your own eyes, this is going to be at the middle of the cylinder. Everything is settled. The only thing we have to do now is to push the coil, press the button, and actually transfer the whole system at the isocenter of the marker. Okay? Under this, okay, there's the point. And now we have actually coincide 3 points. There is only one left, and you can see how this is going to be scanned. Okay? As an extra view, you can see that the phantom is in the center. The cylinder of the phantom is at the center of the cylinder of the coil. It's really nice. Okay?
So let's check the center of the scan outside.
Okay, let's start now. All right, we've done all the procedures as far as the setup of the phantom is concerned. Now we're about to start the scans one by one. We have already arranged the protocol. The protocol is here. You can use it and you can see it's already there. It is called MRI QA, ACR Vision Sonata, which is a machine. We have 2 modes, the standard and the advanced protocols for QA. We're going to use the standard QA. All the sequences are there. We're going to use the head coil. We have a different protocol for each coil. For the head coil, we have already assigned the sequences one by one. So it's already there, it's everything settled. So we're going to go and we discuss what's going to happen at the end. So, first of all, we're going to register the patient, and our patient is a phantom. That's good, okay. We use the reverse date as a code, as an example.
To keep track of the date.
To keep track of the date, exactly. So we got 2017, and we got today's 30th of June, which means we have 6 months, 06, 30. We call it ACR, which is the phantom, and of course this is a QA protocol, okay, QA MR. We need to give the first name for the DICOM, it's there, so the first name is going to be something like test, it's a normal name.
Yes.
And the ID has to do with the thing we're doing now, so it's QA MR, let's say 001, or test. Date of birth, even my birth date, so it's there. So we give my birth date.
So we cannot continue without a date of birth?
That's sure. Reverse again. Okay. The sex is other. Okay,
And the weight?
I'm 54 years, it's there all the time. The moment tells the truth. So the weight now, the weight should be 100 kilos.
This is not true.
This is not true, yes. But why we do this? We do this because we actually want to ohmically load the coil.
Okay.
And that's the idea. I mean, the magnet has to assume that there is a patient inside the ball. So 100 kilos actually is the weight we put in order to load actually the coil.
So it has to do with the transmitting.
It has to do definitely with the transmission of the RF for the coil. There is a whole lecture actually, there's a lot of things there. The point is that the coil or the material, the filling material of the coil has to be appropriately selected in order to absorb the RF.
Okay.
So this specific phantom is been constructed with this film material, and this is actually the thing that we have to do in order to load the coil and let the system proceed to the sequences.
Okay, so 100 kilos will give us the appropriate
The
RF.
appropriate power, RF power, in order to excite, okay, the film material of the coil. Because the plastic part, the external housing, is
Yes.
plexiglass, and plexiglass, of course, doesn't absorb anything. Cannot be seen in a magnet. Everything which is solid cannot be seen in a magnet. So only the liquids have the signal. But the liquids have to have specific conductivity in order to absorb the RF. So the power has to be at a specific level. That's why we use this choice.
So
Now,
the conductivity of the phantom, does it match the conductivity of the human tissue?
we think the constructors say that this should match. Actually, this is there's a lot of there's a lot of papers around. What solution to use? And okay, I got your point now. Actually, this coil, this specific phantom, serves as a material which has the conductivity of tissues and the T1 and T2 of the tissues as well. So that is the point.
Mimics tissue properties.
It mimics tissue properties. Okay, and it was appropriately designed and it's used for let's say 30 years now. So it is a standard in general as a phantom. Okay. Now we choose the study, and in our case, actually we're going to use the MRI QA vision sonata to the system. The patient position should be head first supine. You assume that you actually you have a patient which enters the magnet with the head first. Okay, and it's supine.
I actually saw on the phantom written the chin and the head.
And the head.
So
Exactly.
we
That's the
assume
point.
a patient
We assume that the patient comes with
the
with
supine
head,
position.
the supine position with the head first orientation. Okay. So this button is okay. The exam can start. So we start the exam. Confirm. Actually, the system asks if something is there. All right.
Yes.
So there is something there. That's for sure. The protocol is exactly already there. It's been loaded
Okay.
because we chosen the specific protocol. We start with this. We open the localizer.
Localizers.
The localizers are gradient echo sequences, fast enough, in order to have the overview or the pre-scan of the object. Or the
quick
phantom.
overview.
Okay, the quick overview. That's why they're called scouts. Okay, we hear the sound, actually, and we get the first images of the phantom.
Does it look a bit distorted, geometrically distorted?
It is.
Should we correct for that?
Not for the time being, but I can do it for you if you like. We could do it. All right. Remember that number 2, we're going to correct for linearities there. We know that this system has steep gradients in this case, so we have a problem with that. It's not a real problem because the systems can correct this issue. Okay? This non-linearity problem. How we do this? Actually, we repeat the sequence in this case as it is. We not change anything.
Yes.
And the only thing we put here is we have to use a large FOV. Large FOV means that the system corrects and gives the appropriate colors to the gradients in order to get rid of this distortion.
Okay.
But we have a drawback there. I'm going to do it and you're going to see exactly what's happening. It is a little bit distorted, that's the point. There is a drawback here.
Okay, let's see
You
the new
can
ones.
correct, alright, and you can see it from here. I'm going to go to this, and I'm going to show you the image. You see the difference here. The image is corrected.
It looks correct.
It
yes.
looks correct.
So
Okay,
do we
you can see
use
it there.
the second one for localization?
No, we cannot do it because we change the geometries, and that's the drawback exactly. This is exactly the drawback of the system. So you either have a non-corrected image, and you can use it as a localizer to localize the rest of the scans,
Okay.
or you can have a linear image, I mean a corrected image, but this cannot be used as a localizer
Okay.
because we change the geometry, and if you change the geometry, you cannot have specific. First, as you can see here, you have a problem with the XY axis of the system. Remember that in our definition, in the beginning of this lecture actually, we define the sagittal mode. This is a sagittal view of the phantom, and this is the anterior-posterior direction, which is known as the Y direction. This is the coronal view of the phantom, so you have a right to left or right to left direction, and this is the X-axis. And you also have the transverse view, and in this case you're viewing the y-axis. Okay? Now, as you can see, the phantom is not centered, so we have to center it in order to actually be able to follow the direction of the scan. So, exactly what we do now is we're trying to find the fourth point, which was the center of the scan. Everything, the other 3 points are there. They coincide in one point in space, and now we want to bring the center of the scan to the coincide point of the other 3 scans.
At the isocenter.
At the isocenter of the magnet. So this is called localizer on the center of the coil, on the center of the magnet. Okay, what we do, we take the localizer scan, we unzoom in order to be able to view on all the levels, in all the scans. And that's exactly as you can see here. First thing to have to do is to move actually the center of the slices. You can see here at the cross sections of 3 slices. This is the sagittal slice, this is the coronal, this is the axial. Okay? So we move the center of this slice at the center of the phantom. That's the first point. Then we take the other slice and we put it again at the center. Okay? We can do it digitally. For the time being, we're doing it manually, but this can be done in digital mode. You can use this this window here, this interface window, and you can play with the anterior, posterior direction, left to right direction, and the head feet direction. So we do it manually, not too big of a problem. So we actually scan everything. We bring the 3 centers in one point.
So now we have completed the correct.
We have completed the correct positioning. Exactly. So what we do now, we have the 4 points, which coincide the 4 points of the object, say, coinciding in one point in space, which is the isocenter of the system. Okay? Apply. What you're going to see now, you're going to see everything to shift it at the center of the scans, at the center of your windows. That's the idea. Okay? Big thing? It's true. Okay? There it is. Again, we're dealing with the sagittal slice, then we have the coronal at the middle, and at the right side we have the axial. And everything is in the middle. So this is our phantom, and this is exactly we're ready to start doing the measurements. First measurements we have to do is to use the protocol of the ACR phantom, or what they say. So you have to deal with 2 sequences, a T1 weighted sequence, spin echo, and a proton density, T2 weighted, double echo. Okay? The T1 weighted is standard spin echo sequences, in which is a multi-slice sequence. You're going to see the slices here. There it is. Okay. And according to the manufacturer of the phantom, you have 11 slices with a gap of 11 slices of 5 millimeters thickness, with a gap of 5 millimeters. This is 100% gap. That is designed in Siemens. But anyway, you have a 5 millimeter slice and a 5 millimeter gap in the slice interval. So what you do, you put now, after having set the slices, then you have to shift the slices to a specific position. You have to follow the markers of the phantom now. Okay? So we shift it digitally. That's the best thing to do. We have to shift it in the head feet direction. So we go here, we shift the slice. See the slice moving. It's okay here. Okay? This slice, which is the first slice, has to pass through this entirety, this block, crosses a line here and crosses the ramps here. Okay. So this is the marker that you have already positioned the slices on the phantom, and you are expecting to have specific images. You're gonna, at the end, you're gonna take 11 images. You know from the beginning that you want to see specific visions, specific images. If they're not like they should be, there is something with the lasers. There is something with the lasers. So there is with this test, we also checking the positioning lasers. Right? Then we start. This will take 2 minutes, not that far, right? And then we work with this. Okay. The machine is adjusting. That's what you do. You can hear the sound. We'll explain what this sound, from where this sound is coming from. Actually, you're going to tell about this. You told me. Okay.
So
but
every different slice, every different slice is for a specific test.
Exactly.
So that's why we need to position them where the manual explains to do so.
Yes, you have to position them at the specific points, and you actually obtain images which are going to be used for a specific test in the post-processing mode, in order to measure the whole bunch of quality control tests that you have to do in order to say that this machine works okay. Having said that, there's something also worth to mention here, that this ACR fundum is an accreditation fundum rather than a quality control tool. In the United States, you cannot have an MRI unit operating without passing the test with this fundum. That's why it's been said as an accreditation quality fundum or accreditation fundum, and not just quality control tool. You can find a lot of fundums in the market. It's okay, it's not the only one, that's for sure. But this fundum is being used for the accreditation of departments, not only a machine. Even the specific checks they have to do with the medical physicists like us, with the doctors, physicians, and the technologists. So this is a sort of accreditation in the auditing mode, something which has been done in the States for years now. In Europe, doesn't exist. So, okay, we can discuss about problems as the machine is working. All right.
How often should we perform a quality assurance test?
That's a good question. There are things that you have to do daily, weekly, and quarterly, and yearly. The basic things can be done every morning. Basic things, 10 minutes, no more than that. But you have to have a technologist and you have to have a person which is assigned for the work. Be it a medical physicist, be it a clinical scientist, be a technologist, whatever. This is something that you have to arrange as a medical physics expert. That's a good idea. That's a good attitude. We do a job. In order to do the job, we have to assign jobs to other people. And for the daily quality assurance test, definitely the technologists, when the machine starts in the morning, you need only 10 minutes to do it. So that's a good issue.
So do we keep a log of the procedure?
Yes, of course. This is exactly
results.
the results. This is exactly what is being called quality assurance. It's not quality control, it's assurance. So you do it again, you do it again, you do it again, and at the end you have a curve which actually you can see how the scenario is changing, for example, or how the homogeneity is changing. So that's the idea of the quality assurance. You give the definition. Let's see what we did.
Yes.
Okay, that's a nice image. I like this. Okay, all right. Then you're going to see the whole image. We start by this. Perfect. See the two lines here. If there was a problem with the lasers, this should look like this. So the lasers were not appropriately calibrated. This means that in our machine, our system, the lasers are okay. So I've chosen the specific point in space, and I'm viewing specific structures on an image.
This is the first image of the series.
That's the first image of the 11 slices. The second is this, not an issue. The first image, I'll explain. You can measure a lot of things here, I'm going to show you. Second, it's not that important. With the second, actually, with the second image, you're measuring the contrast here, okay? With the third image, not important. This is important.
This looks important.
This looks important because you actually measuring the spatial linearity with this or the geometric distortions. Of course, this is something that we have to do on a weekly basis or maybe 3 months. This is the point where you can have the SNRs, that's the other part, actually we're the center of the fundum now, right? Okay? And this is the most important issue of this fundum. You are able to actually visualize small holes here, if you can see them. See?
I can now see them.
Yes, you could actually, you could see the small holes here, and these small holes deal with what we call low contrast detectability, low object detectability. And this fundum is famous for this facility. Be able to see, for any sequence you want to design, the low contrast detectability. So this is ingenious design. In order to see, actually, in order to pass the machine, you measure the triplets. You have, for this machine, you have to have at about 36 triplets. Okay, I'm going to show how. 1, 2, 3, 4. You measure 36 triplets. You count the points, easily like that. So if a doctor wants to have a sequence, a new sequence to design, so you have to check all these things, and you have to check and see the low contrast detectability. Is it there? You can see low contrast issues. It's very, very important. Okay, this is what the ACR wants to do, and the second one is the same sequence like the previous one. We actually open the sequence, we copy all the parameters, right? So you again have this, you go to localizers at the center, you go to localizer, right? So you see everything is okay. So we actually copy the position from this sequence to the other. This is a T1 sequence, I told you, spin echo T1. This is a double echo, which is a proton density and T2 weighted sequence. Okay? We start again. Another 2 points. Something like 4 points, I think. 4 seconds. Sorry. Yeah. 8 seconds. 8 minutes. Yes. Okay. It's a T2. It's a T2. This is exactly what ACR wants for us. They want this sequence because they want to change and see the low point stability in T1, proton densities, and T2 weight. Okay?
So we have completed T1 weighted images, PD and T2 weighted images.
You're right. Okay?
How do we continue after that?
All right. These are the sequences that the ACR, we have to do it because the ACR that's what they say that has to be done.
Okay.
So practically, the American College of Radiology wants to have the sequences in order to control the machines. That's the whole story. Now, the next step is to measure the homogeneity of the static field.
Okay.
In order to do that thing, practically, you have to use the sales engineers. You have to call them in order to be able to measure the peak. Do a spectroscopy measurement and measure the spectral peak. According to the ACR manual, this is not the only method. It's really difficult to do it because you have to have the technician, you have to have the service key or the research key. So we have to find another way to do it. In order to do it in a more convenient way, we use the variable bandwidth method. It's mentioned there in the ACR manual. What is the variable bandwidth method? Practically, you're using 2 sequences, in this case T1 spin echo sequences, with 2 different bandwidths.
Okay.
So the first sequence is the sequence with 40 Hz per pixel bandwidth, and this is what we have in here. We're going to take again 11 slices like the other ones. So what we do, we have it here, we open it, and we actually put it in one of the previous sequences. Okay? Localize the same thing. It's there.
We
already.
copy the parameters.
We copy the parameters, and we start with this specific sequence. Okay? This is the 40 Hz per pixel. This is the low bandwidth, as we call sequence. Important to mention also at the start, important to mention is you have one axis, the frequency axis, which is the dimension where we expect to see the differences. So, in this case, our frequency axis is the right to left axis. This axis. Okay?
Is 40 the minimum bandwidth we can have with this
Yes,
sequence?
with this machine. Yeah. That's a parameter which is related with the machine itself. So with this specific machine, the lowest possible bandwidth is 40 Hz per pixel with this sequence. That's okay. But you cannot go lesser than that. It's there. And the far end is the 780 Hz per pixel, which is the higher bandwidth.
So we acquire images at the 2 ends of the bandwidth.
Exactly.
The minimum and maximum.
The minimum and the maximum. These sequences, the images at the end, they have some artifacts. They should be there.
Okay.
With the lower bandwidth, you're going to see the image at the end, and we're going to explain exactly what's the problem. With the lower bandwidth, you have a higher SNR, but you have susceptibility artifacts. Susceptibility is there. With the higher bandwidth, you have lower SNR, okay, but you diminishing the susceptibility artifacts. And you're going to see exactly in the fathom what we mean, where you can see these susceptibility artifacts, right?
How will we image the homogeneity problems of the magnet with the 2 bandwidth images?
How we image? What do you mean? What do you mean? How we image? Actually, in order to do it, yes, I understand. I got the drift. In order to see, visualize the homogeneity of the magnet in this case, you have to subtract the images.
Okay.
So if you subtract the higher bandwidth from the lower bandwidth or vice versa, at the end you end up with something which is called a meniscal artifact or a meniscal sign. That's what we call it. This meniscal sign has a specific width. We're going to show you. We're going to show you exactly what's happening. And from this specific width, you have an estimation of the homogeneity of the field on this direction, on the direction, of course, of the frequency axis, or on the direction that you're interested in. Okay? So you have to wait now. You have to wait 2 minutes for each sequence. So the general rationale is that, first of all, we have the sequence, and you're going to see this with the frequency encoding in the right-left direction. And the image you're obtaining is something like this. We're going to see it here. Okay, that's the image. Remember, we have 11 images of this specific phantom, this phantom. So we go to the first one, and as I told you, we have the problem with susceptibility issues. So at these specific locations, you see this white sign and a dark sign, and in this case, this is being called as susceptibility alpha, which is there. Important also to mention is that from the bandwidth, the difference in the bandwidth, you see the distance between these 2 points. If you go in a standard, let's say, medium bandwidth sequence, which is this T1 weighted, that's why we took that image, at the specific slice, you see that these structures here, actually they are really close to another. This is fat and this is water. I told you that this phantom is really very wisely designed. So with one slice you can have everything. You can see slice thicknesses, spatial resolution, but the important here, you can check the bandwidth of the sequence if you measure the distance of the fat and water. With a low bandwidth sequence, which is here, this distance is increasing. Okay? And this is something which has been described in the literature, it's there. You have the problem. There is also the susceptibility artifact which is here, so you can see these structures, which are high contrast structures, and you have this problem here. And now we'll repeat the sequence with a higher bandwidth, and you're going to see what happens. Okay?
Yes.
We take this is the same sequence again. Be aware to have the same axis, otherwise we're shifting in...
You cannot subtract.
You cannot subtract, that's the point. So we copy all the parameters, we have it there, and now we're about to do the same sequence with a higher bandwidth. The highest bandwidth possible. This bandwidth is mentioned here, 701 hertz per pixels. And you see that the fat shift, the water fat shift is 0.3 pixels, the less possible. Okay? I'm going to show you the same thing, the previous sequence. This water fat shift will change. And this is exactly the water fat shift we're measuring. So you can test with this phantom if that is real or not. It's a good test. Okay. As we already told you, I'm going to actually show you what I told you now. So I have it there, the lower bandwidth.
Yes.
I'm expecting to have a water fat shift 5.2 pixels.
So,
This 5.2 pixels is this actually
so
direction.
this image will show the chemical shift,
Exactly.
while the other one will not,
Will
since
not.
it was less than 1 pixel.
You're right.
Okay.
So with these tools, or with this technique, you are able to measure actually if the bandwidth is okay or not. So this is a good question. The bandwidth that the system says that delivers is delivered, is the real one. So you can check it with this ingenious design. You have fat and water, so the water fat shift is there.
Okay.
You are able to measure the fat shift. It's really very important. Okay, now we'll wait for 1 minute in order to see these two structures at the specific position with the lowest possible fat shift due to the high bandwidth. That's the point. Okay. Questions?
Do we have to
Just answer for yourself, right?
Do we have to do it in other contrasts too? The variable bandwidth method? Do we have to do a T2 scan with
No.
variable? No.
No need. No need.
So the rest of the quality control will be done based on
Based
T1 images.
on T1 images. Okay, this is not exactly true because, okay, that's a good question. In all the quality control tests which are related with this phantom, are going to be T1, except of SNR. In the SNR we're using proton test. Why we're using proton testing? We don't want the material, the film material of the phantom to interact with the measurements. So the proton density actually, you are somehow independent of the T1 related to of the structures there. Because if you go in T1 or T2, these measurements or these images are related to the parameters of the material. So you have to go away from that. So that's why you're using proton density images for the assessment of the SNRs. Okay? As far as the quality control test is there, okay? Can you have it there?
I think we have
You
the new
finished?
images.
Now we have the new images, okay? Let's go and check this. In these new images, I'm going to put it here, and you're going to say, and you're going to see, same slides, what to mention here. Okay, that's a good idea. There it is.
Yes.
Exactly what we're
Okay.
expecting. The fat shift is less than 1 millimeter. It's there. So this is the real structure, and this is the best you can have as far as the MRI is concerned. And you have fat depicting fat and water.
Yes.
That's the best technique you can have on this machine.
And we
So-
have also eliminated the artifact.
The artifact
the
of
edges.
susceptibility, that's exactly what I was
Yes.
saying. So this is the magic thing when you're using sequences with higher bandwidths. The drawback is the SNR. You see the graining actually image of this phantom
More
on this
noise.
specific slide, it's more noise. But you have linearities, it's there,
Yes.
susceptibility is diminishing, and you have depiction of the anatomy as it is, because you have fat and water at the position that they should be. Okay?
At the expense of
At the
SNR.
expense of SNR all the time. Now, we did it for one direction, and we're talking about the right-left direction, okay? Because the
Okay.
frequency is now here. In order to fulfill the measurement, we have to use the other axis, the y-axis. So in the y-axis, already have the sequence. Now the frequency is on the AP axis, it's there, in this axis. So we take this,
So we need the second pair of T1 sequences
Exactly.
with shifted frequency direction.
yes. Now we localize, not, oh sorry. The frequency in the AP. Now you're going to see the difference. These two things, these two structures, we're going to shift the other way,
Okay.
in the y-axis, okay?
Always in the frequency direction.
Almost in the direction, right. So, be aware about, oh, what's happening? Sorry. Open, there it is. Then you take this, put parameter.
We again copy the
Again.
parameters, the positioning.
But then you have to be aware that the direction does not change. The phase encode direction is in the left, right,
Yes.
so the frequency encode should be the AP. Okay?
Okay.
So that's correct. Now we're going to go in this direction,
Okay.
try to find this axis. Right? Let's see what's happening in this axis. Now we shift to the next axis, which is the AP axis, this axis. Okay? Remember that the anterior posterior is the Y.
Okay.
The right to left is the X, okay, and the head fit, which is not measured here, is here, is Z. Okay.
Okay.
In order to measure homogeneity, you have to have an assessment of the homogeneity in the three-dimensional space. So under this rational, this assumption, you have to measure the homogeneity in three frequency axes.
Okay.
So as we're doing now, we're doing the two axes, X and Y, X and Y, and then at the end of the measurement, we're going to shift the phantom in the coordinate direction and check the rest axis, which is the Z
Okay.
axis. Okay? So,
So do we see the subtraction now?
yes, we can do the subtraction, of course, as it's working, just to see it, right?
Yes.
Right,
Yes.
right, we're going to do it. Now, let's check and see what we can do here. All right. We go to the browser, that's what we do. We take these two images, okay, two series, actually.
Series of images.
Okay. You do a subtraction. Important thing to mention here is that you either subtract, you have the operands, you subtract 8 minus 7, which means you subtract the higher bandwidth, the lower bandwidth from the higher bandwidth,
Okay.
in this case. You can exchange it, but for the time you're going to do like this. And you test. You see what's happening here?
Yes. I can
This is
see
the
the
meniscal sign, okay?
Yes.
That's the meniscal sign. You can check the slice as well. That's the important thing of this panel. You can go in number 6, you can test it, and you see what you're expecting to see. This difference, actually, because of subtraction, is an indication of the homogeneity of the system. And if you measure this size in pixels or in millimeters, it can be correlated with the actual ppms, which is a part per million, which has to be, yeah.
Measure the width of the meniscus.
Width of the meniscus, exactly.
Okay.
Important also to mention, if you exchange the sequences, okay, and do a test, this is going to go the other way around, okay?
Okay.
Should be, this algorithmic trick, but you can do it. Also important is you can go in number 4, you can test it, or you can go in number, 6 or 7, I don't remember. Where's the grid? You know, it's not here. I'm going to show you something here. 4, and an important issue. It's 7, 8 probably, no, it's not 8. Now we're going down, so it's number 5. There it is. You know,
I can see a dark circle. Am I
Yeah.
mistaken?
No, you're not mistaken. This dark circle is a partial volume artifact from the next slice. Okay? Remember, there's always a crosstalk between the slices. You can avoid it because you subtract. So you can enlarge this point. Also important here, you see that this shift is changing somewhere here. This means the shift is there, the shift is bigger. if you see. So you expect something like this because you have other things here, but you expect that the homogeneity in the center should be better than the homogeneity on the edges, right?
Okay.
So here the subtraction does not give something important there. You don't see shifts on this axis. Okay. Now, this is the frequency axis. We choose the slice number 6. There it is. We exchange the measurements for the other side. Number 6 again, sorry. And you remember that in the XY axis, on the right-left axis, which is the XY axis, in the frequency axis here, you see the meniscus there. Now we're about to change the axis. We subtract again and see what happens.
Okay, I think we need one more sequence to be running now.
Yeah, we're gonna do it. You know, we have to close it. We're gonna do it. So for this.
So we go for the higher bandwidth.
Okay. Now
Again
we go
at
for the higher
the AP.
bandwidth at the AP direction. You're right. Again, you copy the parameters. Now let's see something amazing here. What is happening? I'm putting. Remember, you have the shift in this direction. Okay.
Yes.
Fat and water.
Right to left.
Right to left. Now the axis should be at the other direction. So I'm expecting to have the shift in the AP direction. And this is the ingenious design. Sorry.
Let's go to the correct
to the correct
slice.
slice.
Here it is.
Here it is. Okay? And
Yes.
then the other one. So you see, they shifted, but they're not shifted in the direction of the frequency equidistant axis. So the shifts up and down is now. With a bigger bandwidth, high bandwidth, actually, you're going to see them at the right position they should be, at the position they should be.
Okay.
Now, important thing is that if I reverse the polarization of the gradient, they go the other way around.
Okay.
It should be.
Okay.
They should go. That's
The
a
one-
very, very important issue there. I mean,
The one which looks down should go higher up.
higher up.
Okay.
So there are a lot of things you can check with this small phantom. I mean, this is very important. Then you see there is also a problem with uniformity here. Yeah, that's probably because of
It
the
looks a
gradients.
little bit smiley.
It looks a little bit smiley, and in fact, I might have a problem with the with the Y gradient.
Okay.
I might have a problem, and I have to compensate my gradients, right? Maybe that is the problem. Okay.
Okay.
Because this is, I haven't seen that thing, a week ago. Sorry. There should be a problem, which is not seen in the other axis. See?
So this is how QA works. We
Exactly.
can track down.
You track down the problems. I mean, you track the problems before they are seen in an image. That's exactly what QA is all about, or quality control is all about, right? Okay.
Yes. So you save
Nice.
time.
You save time, or downtime with the machine.
Downtime, patient comfort.
Exactly. At the far end, you're saving money from the guys,
Money.
the financial guys. You see,
Okay.
that's a good thing. So that's really important. I mean, you notice a geometric distortion here.
Yes.
It's a problem with the linearity of the gradient. We don't have the geometric distortion, although we have the small value.
So
Here,
we have an
next.
indication of which gradients
Is wrong.
suffer from
Suffer, yeah. Miscalibration.
distortions. Yes.
Miscalibration, exactly. Now, we finish the high bandwidth. We're going to put it again there.
Let's see fat and
Let's
water.
see, exactly. There should be, noise is there, should be
Yes, noise there.
there, but
Here
still the
we
same. And as you can see, you have a correction of the gradient itself. You don't have geometric problems. That's the other issue with higher bandwidths. So, if you're going to use the system for radiotherapy purposes, you have to use sequences with higher bandwidths.
Okay, so
Because-
susceptibility artifacts from metal.
For metals, exactly,
Prosthesis.
prosthesis and all the things, they work correctly. They really work nice. So this image and the other, the previous one, the high bandwidth image, is here. You have it there. They should look the same, although we change the gradients. They are the same.
Yes.
Okay?
Yes.
Why to be different? But now you're symmetric. You see, the signal of noise is down. We know that thing. But the gradients are there, so you can correct problems which might happen in the higher, in the lower bandwidth. And you've seen the problems if you take the
Low bandwidth.
low bandwidths at this specific slides.
Here it is.
The frequency is here, left, right. You can see it.
Yes.
And I take the other one here.
Yes.
There is a problem with the wide gradient, that's for sure. Yes, there is a problem. Right.
It looks like.
Looks like we have a problem. So Houston, better problem. We found out why. So it's there. And
So-
then you can pinpoint, you can do the same thing, we're going to do the same thing in the z-axis. So you're going to see if that persists.
Okay.
All the time. Now let's make okay, prior to make the...
So we already have an outcome of our QA test.
Yes, sure, already, live, on camera. That's good, that's good. Now, let's start the proton density sequences for the SNR, I'll explain, and then we'll do subtraction to see the difference in
Nice.
the other axis, okay? Now, again, we go back,
Copy the parameters.
copy the parameters, put it there. I'm explaining this is a proton density image, it's there, it's a proton density sequence,
Yes.
so it behaves like proton density. TR 1000, T 30 milliseconds,
Okay.
behaves like proton density due to the subject, due to the material. But anyway, we start with this, and what we do now, 11 slices again, and we do the same slices twice, okay? In order to be able to measure the SNR in volume, in the whole volume of the funnel. All right? Be aware about this. I mean, all the protocols do say just take 1 or 2 slices. The best thing is to use the 11 slices, according to the
All
SNR
11.
values, all 11 slices. So you have an asset and a measurement in the z-axis. You can have x, y, and z-axis
Okay.
on the fly, with the measurement, right?
With one pair of sequences.
With n pair of sequences. Now let's do subtraction between the two, right? We go here. We go here, sorry. And we're taking the other images. Be aware about this. We're talking frequencies in the right-left axis, okay, and now the frequencies in the AP axis.
Okay.
I'm going to subtract again these two images, these two series of images, sorry.
And expect to
And
see
expect something
a
different.
rotation of the
A rotation of
artifact.
the artifact, exactly. That's good. Now, test it right on. There it goes. Exactly from the other side. So the artifact follows the frequency direction, which is this here.
Okay.
Okay? Now, you can take and check the number 6, which is, as I was saying, and there you measure. Be aware that at the middle, you expect to have a better, let's say, homogeneity. But at the center of the magnet, there should be something better.
Yes.
So if you have a structure here, like we have in the slice number 5, you don't expect to have shift here,
Yes.
because it's better. There is a slight shift, but it's not that much as this one. So with this sort of things, you can have, with this mesh we have there, I mean this structure, we are able to measure homogeneity in all in plane direction. Okay? You can have it there. So at the middle, you not expect to have big shifts. At the edge of the phantom, you expect a shift. And this, again, this size or a dimension is related to the homogeneity of the field for this dimension, right? And be aware this is dimension over something like 190 millimeters. I mean, it's not that big, but
Yes.
you know, in order to be able to measure and say I have an estimation, you have to use spherical phantoms or higher dimensions like 30, 35 centimeters, something like that. Now, what I was about to say, all right? Farme cut, γιατί με κέσαι. Okay, cut, also.
We now have the two identical PDs.
The
Not
two-
identical, but
Actually, that's what they say. I mean, you have one PD, and just after the one sequence, you're taking the other.
okay.
So you have to maintain the time. You have to do it after 2 minutes, actually. So if you leave that thing a long time, you take again at the end of all this,
Okay.
you're gonna see some differences in subtraction. So practically now we have to subtract those two series
Okay.
the way we do, exactly the way we did with the variable bandwidths, right?
What
So
do
you
you
have-
expect to see?
That's a good question. What do you expect to see? You expect to see the difference between two signals. So at the end, you're going to see something which looks like you take the subtraction. I'm going to show now. Again, you have 11 slices. You have to choose which slice. We go to the 6th slice, which is
The center.
the center. You test. This is perfect for me.
I can see nothing.
You can see nothing. That's what you're expecting. There is some high noise here, which comes from the low coefficients, the high coefficients. That's what they say. But you don't see any ghost here.
No.
So it's practically a really nice image as far as SNR is concerned. An important thing here is you can save the images to make the whole post processing. We're not going to do post processing now, but at least we see what we want to see. Let's move to the other slices. Go to the edge of the image, for example, and see what's going on. You see some distortions at the
Yes.
edge, should be there. You take the one edge and the other edge, okay? Test again. I'm satisfied with the image. So you have a sort of something, which is nothing,
Yes.
but it's not really nothing. Because in the MRI, nothing is nothing. So even air can have it there. So, and you shouldn't expect to have, let's say, a flat image. Otherwise, there's a ghost. There's a small ghost here.
Yes.
But in this case, in this machine, as you can see, SNR is actually, we are going to measure it, but anyway, just visualizing it, you can see it's okay. You can save this image as an SNR in order to try to measure it. You're going to do it
At the post-processing
at the post-processing,
stage.
okay? All right. You save this SNR.
Okay.
Important also issue here. There is a button here, it says auto scale.
Should we
So
press
you do, yes, we have to, it's the difference, okay? You let the system to do an auto scale on the images in order to view an image which looks like this peak, okay? And this is actually the Gaussian distribution that we're expecting. When you subtract two signals, at the end you end up with something which is called, this is the difference image, okay? And in this difference image, the signal is auto-scaled, so it shifts from zeros up to a value,
Okay.
and the shape of this line looks like a Gaussian line. So you have negative values, you avoid the presence of negative values. I'll explain it. It's really important. If I take auto-scale off,
Yes.
okay, you see I'm shifting near zeros.
Mm-hmm.
All the magnets in the world do not display negative values.
Yes.
That's the important thing. If they do not display negative values, then if you do the measurements, you exclude zeros.
Yes.
You have only positive values.
Yes.
So actually you have half of your noise here. That's why you do the auto scale. We shift the images, the difference image. We shift the scale to a positive value, that's what it does. So here you see all the distribution of the signal, of nothing actually.
In order to have the rest of
In
the
order to have the rest of
distribution.
the distribution, exactly.
Okay.
And that's the trick. You are measuring on this image, this subtract image, and not in the other one. So I'm going to put SNR2 in this case,
Yes.
right? In order to see the difference when we make the statistics. Okay? Oh, that's okay. Now here you're going to have two images, SNR1 and SNR2, practically. Let's do the refresh. Yep, there it is. This is the SNR2. Now let's try it again. We're going to save the SNR1, which is the unscaled image, right?
Okay.
Alright. Do it one more time. Evaluation, dynamic analysis, subtract again. We're going to test. Take this thing off, alright, this image, and I'll put it as SNR1 to remember, right?
Yes.
Then, okay, you save this. And we know now that SNR1 is without the scale, then SNR2 is with the scale.
Okay.
To see what we get in other statistics, it's important. Let's do the refresh. Yeah, you remember this.
Here it is.
Alright. Now, prior to go to the post-processing of these things, because it's easy to do it with the machine itself, the software itself, you can do it easily. I'll explain. Then we go to see the slice thickness. Slice thickness is a normal bandwidth sequence, is a T1 sequence, it's not the problem density now. Again, 11 slices. Again, alright, important here. This is with slice 3 millimeters.
3 millimeter slice.
3 millimeter slice, appropriately positioned with the distance factor, in order to have 11 slices positioned at the same point. We shift the slice thickness, we diminish the slice thickness, but we want to put the slice thickness at the center position of the 11 slices, of the phantom. So this is important to mention. I mean, you have to actually change the distance factor in this way, appropriately, in order to increase the gap between the two, in order to put the sequence at specific locations, right?
So we leave enough space to accommodate for thicker slices.
For thicker slices, exactly.
At the next sequences.
At the next sequences.
Okay.
You're right. That's the thickness 3 millimeter slice. You start with this, again 11 slices, all right? And then I'll take another one which is numbered 2 millimeter slice, right? And then we do the analysis for the SNR, right? All right, okay.
Even further apart, yes.
Even further apart, exactly.
Okay,
They are
distance
there.
factor of 400 now.
Exactly. Again, we copy the parameter, shift in the middle.
Yes.
You can change with the distance factor as the change of slice thickness. You diminish the slice thickness, you increase the distance factor. But you have to maintain the slice at the same position.
We always have the center of the slice at the same position of the
At the same
phantom.
position of the phantom, exactly. Or the 11th slice.
Okay.
It's there. So let the system work. We're going to make some measurements on the SNR, right?
Yes.
Remember the SNR1 and the SNR2. There it is. Yeah, we can see them.
Yeah, I can see them now.
You can see them down. All right.
Yes.
This is, we want to have the 6 slice.
Dark background is for the shifted,
Yeah. No, white background is for the shifted,
the gray.
the gray, and the dark background is for the 0. Is for
0.
the
Yes.
non-application.
Half of the noise.
Half of the noise. Exactly. Now let's go. I'm going to see exactly what I mean. So you go to the slice number. Let me check. I have to have the same slices. And I'm going to take the PDs. This is the difference. And this is the PDs, right? The 2
Yes.
PDs.
Yes.
You check slice number in the middle. This is number 6. Here it is. Study 1, and you have image 6, okay,
Yes.
from 11.
Yes.
Now we put the same position here. 1, 2, 3, 4. Measure here. 5,
5,
6.
6.
There it is. 1, 2, 3, 4.
Here it is.
There it is.
Yes.
Now, according to the NEMA definition of SNR, in order to measure the SNR, you have to do the specific things. First of all, you take a ROI,
Yes.
and circular ROI. And you put the circular ROI somewhere covering circular ROI, covering the 80% of the image. That's your signal. Okay? You can actually shift it somehow. You can check. Yes, some here. That's why you have this marker here. This marker is an indication that you have to measure at the middle of the phantom.
Okay.
So that's the instruction. What you get in here, you get in the signal, and as you can measure, the signal is 1,486,
Yes.
okay, plus or minus 55. You don't mind about this. So
Okay.
your signal plus background is this, something like 1400. Okay.
Yes.
Then you take this ROI, you copy it, you go here, and you paste it there.
Yes.
Do it again here, paste again. Same ROI,
Yes.
shift it to the background, to the subtracted image.
Okay.
What you take in here, you see you have the mean and standard deviation,
1.8.
1.8, and here you
Compared
have
to
8.1.
8.1. Reverse.
Reverse. Can you imagine the difference?
Yes.
At the end, if you divide this, that's what we do. You divide this with the standard deviation of this, and you divide this with the standard deviation of this. The difference is, you have a tremendous difference in the measurements.
Yes.
So you go, you say the signal, and your noise is the standard deviation of the subtracted image, which is 18 here.
Yes.
Here is 11. At the end you have wrong measurements. So the right measurement is to scale up everything
Yes.
and take the ST of the scaled measurements on the subtracted image. It is very, very important because you keep your distribution on a Gaussian level. Because here you're dealing with something which is called a Rayleigh level, Rayleigh distribution. This is the Rayleigh.
Okay.
Because you exclude the zeros, right? You take off the zeros, and according to what they say, you have a bad estimation of SNR, a wrong estimation of SNR. Okay? So, important issue to mention here is that with this method, which is a NEMA method, that's what they call, this is the NEMA method, right?
Yes.
You are able to actually measure SNR with any coil you like. This coil is a 2-channel array coil, that's what they call it, 2-channel. You can have 8 channels, you can have 15 channels, whatever, 16 channels, 30 channels. This method is always the same,
Yes.
because you subtract one from the other, and at the end, you're sure that what you're measuring is the real SNR. You don't need to correct for the other elements. So this is the beauty of this technique. There's also another technique, they call it practical method, but okay, this is far more easy. From the same image, you are able to measure the SNR, and of course this is unpractical for the clinical purposes, because you have to repeat the examination twice for the patient. Things are changing, so
Yes.
you're not sure that what you're measuring is real SNR or noise. Okay,
Yes.
so with this the phantom doesn't move, so you're there. All right? Okay.
Nice.
Now let's see about the thicknesses now,
Yes.
and how slice thickness can be measured actually. All right?
In the meantime, maybe we can put the thicker slices.
Yeah, of course. The other ones. This is
Yes.
the, okay, you have the
1.1.
This is, let me check, what is this? Yeah, this is my, okay, I'm playing here. Alright. This is, okay, this is the, I mean, yeah, you want to make them down? No, make them down, right? Alright, let's check this. We've taken all the slices, all the slice thicknesses, different thicknesses. Now we're going to check and see the effect of the slices. So let's start from the beginning, alright? This is the 5mm slice,
Yes.
right?
The bright signal is from the ramps inside the phantom.
Exactly. This is the method you actually using to measure slice thicknesses. So you
Okay.
use crossed ramps. That's the thing you have. What you're measuring practically is this distance of the bright areas. There are a lot of things in post-processing that you have to take care about this. It's not the time now to discuss, but practically that's what you do. You can have the profile of this thing, you can have a line profile of this, line profile of this, okay, and then you do an algorithmic subtraction of those two, and you measure the slice thickness. For this specific phantom, the ramps have a specific angle between them,
Yes.
and that's why actually practically you can measure it easily. You don't have to apply a mathematical formula which is, we take into account all this tangential stuff. Anyway, this is the 5mm slice and you have this size. Now we go to the 3mm slice. The size is changing.
It's
The
narrower
shift is
as we
narrower
expect.
as we expected, exactly,
Okay.
because the slice is changing. It's getting
Yes.
less. The 2mm slice,
This looks
and this looks a little bit better.
Even smaller.
Even smaller.
Yes.
Okay. And the 1mm slice. You're able to measure it.
Yes.
This is something you have here. Okay.
Okay.
We don't the perfect localization of the phantom at this level, but you have to have into account the shifts in 3 dimensions, right?
Yes.
Should have the slice, the upper part, being the same as the lower part. So they should follow this, let's say, orientation. Okay? They should be close.
Yes.
But you can imagine now, if there is a small shift or a small tilt in the Y or the Z, actually they change it. You don't mind if this are shifted apart. They don't maintain the center. Okay? You don't mind. The only thing you mind is to measure this profile, this size. Okay? And this is the 2mm slice. We're going to go with the 1.1mm slice. Okay? And they change it. They recommend not to go that down. I mean, use it and keep it up to 2mm. Okay? If you want to go in lower slices, then you use 3D sequences.
3D sequences.
Otherwise, you're mixing the problems there. So you're mixing the words. That's what I say. Now there is the last check left, which is called high spatial resolution. All right.
Okay.
I'll take this thing here. Again, we repeat the 11 slices. I'm taking something like here. All this T1 contrast. Use T1 only. Here, beware, we put a resolution of 512, okay?
Yes.
And this 512 resolution, of course, you expect the time to increase 4 minutes, it doubles the time, but the pixel goes down to 0.5 by 5 millimeters.
Okay.
So I'm expecting to have a better resolution, spatial resolution, and being able to see the dots here. You're going to see. You have to wait something like 4 minutes, right? Let's make a calculation. Now, as for a spatial resolution, this phantom is designed in a way that you visually inspect the resolution. So these sizes here, I'm going to zoom it a little bit. Maybe zoom somewhere. Yeah, I'll zoom it from here. There it is.
Are those dots at the dimensions of the pixel?
Yes,
If we have a matrix of 512.
exactly. Now, according to the phantom, this is 1 millimeter. 1 millimeter pixel. This is 1.1. This is 0.9. So you have all the pixels and you have the depiction of them. If you actually scan with the pixel dimensions equal pixel dimension about 1 millimeter, 0.98 millimeters, and if you scan with the dimension of the pixel being the same as the dimension of the structure, you expect to see something like this. You see it, you do not see it.
Yes.
So if you scan with double, with the lesser pixel, 0.5, half pixels, then you will be able to actually visualize the whole structure there. And you sure that the machine, when it says I deliver a sequence with 0.5 millimeter slice thickness, it's there. Oh, sorry, 0.5 millimeter pixel size. You have it there. So that's an easy way to visualize what you're doing. Okay?
Provided that your eye is also a powerful
Of course.
screen.
If you don't have problems with your eyes. You're right. Okay, I think this is the last check we have to do. There's a lot of work to be done in the post-processing mode. Of course, the post-processing with these machines and generally the machines that we sell that you can use, you don't have that for much facilities. So you have to shift them to other workstations.
Okay.
You name it. Sort of, a lot of software works on these areas.
But you can find a free software to continue with the post-processing,
Yes,
right?
of course, MRI. Yeah, you can use this is what I like. You can use the slicer 4, slicer 4.5. It's there. You can use the MRI there. It's free. And I think there are other software. I don't remember. There are some softwares you can use really fast.
Yes.
You can even use MATLAB. It's free. It's not that free, but anyway, there's a version which is. But of all I know, I think MRI is the best. We use MRI for this sort of things. So you can measure the slice profiles. You can do some things. You can measure the ROIs. You can do a lot of things with the MRI. And you can also have maps with the MRI. You can calculate maps. An important issue here is, that's a question for you now. What would be your suggestion if I was about to measure the SNR for each pixel, not for a ROI? What would be your suggestion? Could I do that thing? Could we do that thing?
As far as the
Because
SNR1 or SNR2 is concerned?
Yeah, okay, let's say we use the SNR method, the SNR2 method, which is you scale. You have to be alert, you have to know that we're measuring SNR of this specific area, okay? So we have a large ROI,
Yes.
that's what NIMA standards recommend, right? But my question goes, if I was about to measure the SNR for each pixel, this method, you think that this method will help? Would be the convenient one? Or not? Okay, I'll ask the question.
Please
Right.
give me a hint.
I'll give you a hint, right? Okay, the hint is that the practical method, I didn't tell, is the one that you have to use.
Yes.
I mean, what is the hint? The hint is, if you work with subtractions there, subtract pixel by pixel, then you're missing the SD if you have one only pixel.
Right.
You're missing the SD. You're missing the SD because you don't have areas to calculate this.
Yes, yes.
That's
you
the
need a
crucial part.
distribution.
You
for
need a
SD.
distribution.
Yes.
If you
okay.
don't measure, you are not able to measure distribution of pixels, if you didn't want to do one pixel, then in this case you don't measure SNR.
Right.
The alternative way to do it, and you have the thing that we call as SNR map on the
Yes.
system, is to use the other method, where practically you are measuring noise outside the image. Okay?
Okay.
Important also to mention here.
So
Yeah.
for pixel-based analysis, you need to have
Yeah, the
the
method.
second method.
The second method.
Okay.
You measure the signal in a pixel, okay, and then you take a ROI of the background, which is actually the estimation of noise from the background to the same image.
Okay.
Right? So there you are able to find the SD because the SD is the same for all the pixels. That's the way. And
So I
that's the
believe
clue.
we have to avoid the artifact areas of the face direction and have a ROI.
Yeah, that was about to tell, and we can have a discussion about this. But we can wake up in the morning. But this is a good idea. I mean, when you're about to use the other method, the practical one, where you're measuring the SNR from the same slices, you have to be alert that you have to choose an area outside the image and outside the face ghosts.
Okay.
So you have to know where the face is. That's why I burn the image with the contrast. I know that the face is there because you see the artifacts, okay? So if I'm about to measure the SD of the noise, you have to put it up there or even parallel to this axis, which is outside the face, outside the face ghosts, right?
Yes.
Another tool we use is we can measure the face ghosts, okay? And there is a test that we have to do processingly. At the far end, we're finished because this is what you have to actually use. All these images should be used and moved in a workstation and make actually the measurements in order to fulfill the report.
Okay.
So thanks very much for your attention, all right? So you have something to say, have you not said
Thank you
now?
very much for all the nice things we learned.
That's very nice. Okay, all right. Okay, now there's something left, sorry. Yeah, we haven't seen the last image. That's the last
Yes.
image.
Let's see the. Oh,
It looks really nice, all right? it looks really nice.
We can see the difference with the 512 matrix.
That's the 512 matrix. So you are able to see, because your pixel is less than 1 millimeter, so you're able to resolve the points here, to resolve the dots actually. It's clear. Things you cannot do with this phantom is you cannot have MTFs and measurements of the system itself, the resolving power of the system. You could not do it. But you know, you have to use other phantoms for that. As a practical tool for doing basic quality assurance tests, I think this suffices. It's okay. So thanks very much all of you for attending us, right?
Thank you very much.
Close it down. Νομίζω τελειώσα. So that's all, folks. We have to say that we have finished all the procedures. I think you learned some things about the whole procedures as far as quality assurance is concerned. We have to say goodbye. It's really late. So,
Goodbye from me.
okay.
Thank you very much.
Thanks very much for this meeting. That's really nice.